All right, 14 quick examples using special right triangles and Pythagorean theorem. Starting off with this first one. Now, I didn't say what type of property you should use for each one of these. You got to kind of look at the problem and see if you can identify whether you have a special right triangle, whether you have Pythagorean theorem, whether you have a Pythagorean triple. So I haven't given you guys many of the triples yet, so you might not recognize some of the triples. Now, on this one, I'll tell you for number one, I don't think it's going to be a triple. So I know I have two sides. You can always go to Pythagorean theorem if you have two sides of a right triangle in order to solve. So for this one, I'm going to plug it into Pythagorean theorem. I have x squared. I'm using x as my c value because it's the hypotenuse, equals 12 squared plus 15 squared. So again, you need to try to get better with your perfect squares because it'll help you out. You could do a problem like this without doing any calculator. So 12 squared is 144. 15 squared is 225. Add those two together. You have, let's see, 5 and 4 is 9. 2 and 4 is 6. 2 and 1 is 3. So we get 369. Now, I was actually wrong because, oh no, I'm thinking 396. No, this does not work out. So this one is not a Pythagorean triple. We could reduce this though. So a number that I know goes into this, I know 9 goes into this. And the reason I know 9 goes into that right away is there's a trick with 9s. If you have values that multiply together to give you 9, sorry, I said that wrong. Add together to give you 9 or a multiple of 9, 9 must go into it. So like 3 plus 6 is 9. 9 plus 9 is 18. That is a multiple of 9. So I can split that up just like we were doing in the last section, because our last step here is to take a square root. So if we take the square root of this, we're going to have 9. And let's see, if I divide this by 9, 9 goes into 36 4 times, 9 goes in once, and 41. 41 is a prime number. Can't break that up. Square root of 9 is 3. So we have 3 radical 41. And that's a good answer. Again, we want to start leaving our answers in terms of radicals if we can. So that's an exact value. I should leave it like that. But number 2, same idea. I have a missing value. This time it's on a leg. So that has to go in as either my A or my B value for Pythagorean theorem. So 10 goes in for C. So 10 squared equals, doesn't matter where I stick the other 2. 10 squared is 100. 7 squared is 49. Subtract 49. That leaves me with 51. Well, square root of 51. 51 is a prime number, so it's just going to stay square root of 51. That's my answer. So again, you can leave it as a simplified radical. Sometimes you don't even have to simplify anything because you can't. On the next one. Now, you might recognize, hey, we have 5 blank 13. If you recognize the Pythagorean triple right away, I don't have to show any work on this problem. I can go right to saying, hey, this is definitely 12 because it's a right angle. 5, 12, 13 is one of my triples. Now, if you didn't recognize the triple, could you use Pythagorean theorem? Of course. It would take you longer, though, and as the year goes on, you're going to be wasting a lot of time if you don't know your triples. So, for z down there at the bottom, let's see, 13 squared, that's 169 equals 5 squared is 25. Oops, that's a plus sign, not a equals. Subtract the 25, you get 144. Square root that, and you get 12. Alright, so again, whether you recognize the triple or not, you should still be able to do that problem using Pythagorean theorem. Now, on this one, now we have some angle measures in here. They're there for a reason. This is telling us that we can do our special right triangle. We have it 45, 45, 90. So the two sides that are across them 45-degree angles must be congruent. So these two are the same. So A right away I know is 2. B is always going to be the leg times the square root of 2. So this one is going to be 2 radical 2. And that's it. Those are my two answers. no real work to be done. You have to have the properties memorized, because 45, 45, 90, if these two are x, this one is x radical 2. That's a property. All right, on 5 and 6, you have, again, 60-degree angle, so that means this must be a 30, 60, 90. So we have the hypotenuse, which again, this is our property. I'm going to go ahead and write it down here. Short leg is x, hypotenuse is 2 times x, long leg is our short leg times radical 3. So if this is 12, that's the one that's double the short leg, so divide in half. This piece is 6. And if we know the short leg, then this piece is the short leg times the square root of 3. Those are our answers. Not a whole lot of math to actually do there. You just have to know your property. Again, memorization. On number 6, same thing. We're going backwards. So this is the same property that we had up here. The triangle's just tilted. Right? So x, x, x radical 2, those are our properties. Well, we have the x radical 2, so 5 must be x. Therefore, both E and F are 5. Again, if you know your properties, no work. On this one, now this is tricky. All right? Notice, it's very similar to the last one. How did I actually get rid of that square root of 2? Well, you divide it off, right? In order to go backwards, instead of multiplying by square root of 2, you divide by square root of 2. So here, for this section, you might not know how to do that. So I'm going to guess if you ran across a problem like this, you might actually do it in your calculator. 10 divided by the square root of 2, which is going to give you, as a decimal, 7.07. So that'd be G. Now, tomorrow in class, I'm going to talk more about rationalizing the denominator, because we still want to be able to give an exact value on this. However, our answer that we got here of 10 over radical 2, that's not a good answer. You cannot leave it in that format, because you're not allowed to have a radical on the bottom of a fraction bar. You cannot have radicals in the denominator. So the way you get that out is you do what's called rationalizing the denominator. In order to get rid of a radical, you have to multiply it by itself, essentially square it. So whatever you do to the bottom, you also do to the top. Once you do that, the top is now 10 radical 2. The bottom is now, instead of square root of 2 times square root of 2, it's just 2. Because square root of 2 times square root of 2 is square root of 4. Square root of 4 is 2. And now we can reduce this. 10 divided by 2 is 5. So we get 5 radical 2 as our final simplified radical. Now, there is a shortcut. Anytime you divide by a radical, it's always the same pattern. You'll always take the number that you're dividing, and then take what you're dividing by, divide that number by what's underneath the radical, and then multiply by the same radical. So notice, if I took 10 over the square root of 2, I'm going to take 10 divided by 2, I get 5. Multiply by the same radical, square root of 2, 5 radical 2. That's it. That's my final answer. Come over here to number 8. Again, I'll show you more with rationalizing tomorrow in class. On number 8. Let me go back for just a second. 7 and 6, they didn't have angle measures there, but there's other things that told me that this was a 45, 45, 90 triangle. This one, we have the congruency marks, so we knew it was an isosceles right triangle, which makes it a 45, 45, 90. On this one, these two sides were both G, meaning that they're the same, therefore it's an isosceles right triangle. Again, 45, 45, 90. For this one, again, we got the 30, we got the 90, so this one must be 60. This is our short leg this time. Again, it's facing a different direction. So if you need to, draw it out. That's the short leg, that's x. The long leg is x radical 3. This would be 2x. So we know x, double it. That side's 10. This side's 5 radical 3. Now I forgot to label those with variables, but again, you're finding the missing sides of the triangle, so we just found both the missing sides. All right, that's it for that type of example. But now I also want to take a look at saying whether a triangle is a right triangle or not. And then if it's not a right triangle, well, is it acute or obtuse? So looking at the first one, 7, 24, 25. Now, if you know your Pythagorean triples, and there's a lot of them, you might be able to do this a little bit faster by just saying, hey, these are Pythagorean triples. Look, this, well, you can't really see that too good. Let me hold it up. This is a list of a lot more Pythagorean triples than what we covered in class. And if you'll notice on this list, 7, 24, 25, that's a Pythagorean triple. That must be a right triangle. You don't even have to do any work. If you recognize the triple, you can just say, it's a right triangle. And you could say, if you're asked for a reason, it's a Pythagorean triple. That'd be a good reason. Now, if you didn't recognize it right away, then you have to do the work. So 25 is the biggest value. You go in for C. So again, C squared equals A squared plus B squared. 25 squared equals 7 squared plus 24 squared. So you'd have 25 squared, which is 625. You'd have 7 squared, which is 49. And you'd have 24 squared, which is 576. Add those together, and you get 625. They're equal, therefore it's a right triangle. Again, if it comes out equal on both sides, it's a right triangle. Now, number 10, 5, 7, 10. Well, again, if you know your triples, you might look at this right away and be like, hey, that can't be a right triangle, because if I had, sorry, I said 5, 6, 7, 10. That can't be a right triangle because this, 2 of those fit the pattern of our 3, 4, 5, but doubled, right? So 3 doubled is 6, 5 doubled is 10. So if this was a true triple, 4 doubled would be 8. So this is not going to be a right triangle. Again, you might not know your triples yet, so you might not be able to say that right away. So we could plug into Pythagorean theorem and C. So we have C would have to be the 10 since it's our largest value, equals 6 squared plus 7 squared. 10 squared is 100, 6 squared is 36, 7 squared is 49. Well, 36 plus 49 gives us a total of 85. So 100 is greater than 85. Well, that means that if the C squared value was greater, this is obtuse. That's an obtuse triangle. On this one, 4, 4, 5. Again, I don't know right away by looking at it, so plug it on in. We have 5 is the longest side. 4 squared plus 4 squared. 5 squared is 25. 4 squared is 16. 4 squared again is 16. Add them together, you get 32. Oops. 25 is less than 32. Well, if C squared is less than, it's an acute triangle. Number 12. Again, this is another one of those Pythagorean triples. It's not one I showed you in class, so you probably wouldn't recognize it. But if you look at the list, there it is right there in the top corner. So this is a Pythagorean triple, so we know it is definitely a right triangle. If you didn't recognize it though, again, you could have used Pythagorean theorem to figure it out. So 17 squared is equal to 8 squared plus 15 squared. So, showing work on that one, you have 17 squared is 289, 8 squared is 64, 16 squared is 225. Add those two together, and you do get 289. This one, as well as the last one, it is definitely a Pythagorean triple. Again, it's on my list here. There's quite an extensive list. I'll show you more of these as we go on, and I'll post some of these to Edsby as well later on. But 9, 40, 41 is a Pythagorean triple, so this definitely is a right triangle. If you didn't recognize it as a Pythagorean triple, you'd have plugged in 41 squared is equal to 9 squared plus 40 squared. Again, base value always goes in for C. Now this one I actually need to use a calculator because I don't know 41 squared off the top of my head. That is 16 81. 9 squared, I know, that's 81. This one I could do in my head, that's 1600. Add those two together, and guess what? We get the same value because it is a right triangle. The last one, I don't recognize it off the top of my head, but before we even plug in, there's something wrong with this. I want to know, is this a right triangle? Well, I know right away that this is not a right triangle. In fact, this isn't a triangle at all. So I can't even plug into the Pythagorean theorem and use the converse to see if it's right, acute, or obtuse, because this does not make a triangle. So, not a triangle. Now, why would it not be a triangle? Look at the values. 3 plus 4 is 7. We had a property, an inequality property for triangles, that said any two sides have to be greater than the third side. 3 plus 4 is only 7. It's not greater than 8, so this can't be a triangle at all. So I'm going to write that down here. Totally separate from what we were doing today with the Pythagorean theorem, but it is a property that you would have to know that 3 plus 4 is not greater than 8. Therefore, it can't be a triangle. All right, and that's 14 problems in 16 minutes. Again, make sure you do your assignment tonight. A couple things that people found. There are some problems from the Student Companion book that you could skip over. Some of them asked to do proofs. I do not want to do proofs in this section. Didn't mean to sign any proofs. So the homework assignment, again, was from number 2 all the way through 22. I originally had you just skipping number 14. Now you can also skip 17 through 19, because 17 through 19 all deal with proofs. All right, that's it. Good luck.